welcome you to another statistical learning class. Before I get started, I want to make this announcement. I've already updated the solution. I was looking into the solution that I posted yesterday on Midterm 2, and I observed that um, that was an incomplete solution. So I've updated that so you can check the announcement. Sorry, the model. So you're actually going to have your booklet back on Friday because when I'm done with grading, I used to have an extensive review if I probably make a mistake or not. So today we're going to continue from where we stopped. On Monday we started regression trees. Okay. And of course, we're going to consider other form of non-linear models. So let me tell you this. We'll talk about regression trees, whether the one for prediction or the one for classification. Assumption is that, the relationship between variables is non-linear. Okay, so um, but for you to be able to understand, the new modules that I want to walk you through today, I'm actually going to have a recap on what we did on Monday, because understanding what we want to do today depends on what we did on Monday. So what we did on Monday was a special form of what we want to do today. So let me just give you the models. We have what we call regression trees. We have regression tree for prediction, for classification. For prediction is when the response variable is continuous. For classification is when the response variable is categorical. Now, whether for prediction or for classification, we are only building one single tree. Okay, we're building a single tree. Okay, we're actually building a single tree. Okay, so I'm gonna say this again. With a regression tree, we are only building a single tree. Now, when we build a single tree, okay, except that, on the single tree, of course, we know what do we have on a tree? We have so many leaves. Okay, the leaves that we have, okay, actually represent what I call the terminal nodes, the leaves that we have on the tree. Before we can have the leaves on the tree, we actually going to have create multiple regions. Okay, I'm actually going to call them non-overlapping regions. And now I'm going to create them. I'm going to create them based on splitting the predators. I'm going to split predators, so which means you know we're going to construct multiple regions that actually correspond to the values of predators. Now, when we do that, we have to be careful because we want to have less split. More split will make that tree to be overgrown with so many leaves. Okay, so when a tree is overgrown with so many leaves, that will create room for a problem of overfitness. Okay, and one of the way we can use to correct that, because that will be based on certain selection criteria where we're going to say, okay, we don't just continue to split, because when the more split will lead to more leaves and your tree will be overgrown. There should be a point where we're going to stop. Okay, and that's what we call stopping rule. We call that stopping rule, where we're not going to have no more than five observations in the particular region. And at times, we make use of minimizing residual sum squared, but the reason why residual sum squared may not that be trusted is because there's possibility if I have two um trees that are nested and they have similar residual sum squared, because when you are conducting a nested if test situation where there is no appreciable difference between a nested and complete, I mean between a simple model and complicated model, you're going to settle for simple model, right? So if we use that approach, we're actually going to mix a particular split, and that very split may be the one that may lead to a drastic reduction in the residual sum squared. And that is the reason why I remember on Monday, and I said we can also base our decision on text mean square error. Okay. But so if you want to use a test mean square error, you're going to use that through cross validation. But with cross validation, you know, the process, the computation process will be complicated. And that was why I made a suggestion of another technique that will call complication pruning. The complication of pruning will actually behave like a lasso version, where we added additional penalty to the model that will do the pruning. Okay, so I remember, and that was why we actually going to have an ROSS. I think I told you on Monday. We actually uh, minimizing the ROSX, okay, and there's going to be alpha and the absolute value of t. The absolute value of t will be probably the optimal numbers of leaves that we're going to settle for at the end of the day. So initially, when we start the tree, we're actually going to have this guy T0. T0 is we will allow the tree to be overgrown, but we're not going to use T0. Okay, for any value of alpha, okay, it will correspond to a subset of this T0 that we're going to use at the end of the day. Now, that is, regression tree for prediction. Now, the one for classification, of course, uh, we're still going to have ROSS. Oh, sorry, we're going to, instead of ROSS, sorry, we're going to have error rate. And when you have the error rate, we can still consider that very penalty. And of course, we're going to assign observation into the class with the maximum posterior probability. But you know what? What is the limitation of that? Because in statistics and in statistical learning world in general, we normally move to exploit different kind of models where we observe there's a weakness in a particular model. So what is a weakness in regression tree? I needed to pay attention. The weakness in regression tree, because you are using a single tree, okay? A single tree to me is more or less looking like you considering a point estimate. In statistical analysis, a point estimate could be wrong or right, it could be high or low. And that was the reason why we normally go for interval estimate, right? That is more or less synonymous with that, because a single tree could overfit. I'm going to say that again. A single, tree could overfit. And that is the reason why we're now going to consider the other form of the model, nonlinear model, that we're going to call bagging. Okay, now bagging is going to be a generalization. Now, before moving into bagging, because the essence of moving into bagging and random forest and boosting is for us to be able to solve the problem of over fitness that we are likely going to experience with the regression tree. Don't forget, we're only building a single tree. Now, but before moving there, whenever you are seeking relationship between variables, um, when the relationship is linear, of course, you need to go with a linear model. When the relationship is non-linear, then we can think of, fitting all of these. So that is what I'm actually trying to talk about. And we have a way to investigate the performance using the estimated test error. Now, I'm going to come here right now. I want to say other form of models that we can consider, okay, in a way to solve the problem of overfitness that we observe using a single tree in the regression tree is when we consider bagging. Now, don't forget, what led to overfitness is high variance, okay? And that was why I said here, if you take a look at, I said, unfortunately, in practical application, trees often suffer from high variance. And high variance is not good for prediction. It's not good for predictive accuracy, okay? So whether for regression purpose or for classification purpose, and we believe that bagging, random forest, and boosting will be able to correct that because we are looking for opportunity to increase predictive ability. Now, I want to walk you through bagging, but you know what? Bagging is a generalization of regression tree. Regression tree use only single tree, okay? But bagging, we actually train on multiple trees. But I'm going to tell you, how it's going to do that. It's going to do that by bootstrapping. You remember what we've done before? We've done bootstrapping. So what we're going to do, if you have original data set, okay? For instance, if I have 5 data set, I can bootstrap. I can have so many. I can have 1,000 bootstrap from the data set. What do I mean by bootstrapping? I'm actually going to be doing that sampling with replacements. Okay. And you know what is going to happen? You're now going to train regression tree on each of the bootstrap. Okay. Now, instead of having just one tree, then you have so many trees. And let me tell you how this is likely going to solve the problem of high variance is because the fact that you are using more than one tree, if some trees actually overfit, some trees will underfit. On average, on average, it will be fantastic. Okay, that will be better than just using a single tree. Okay, now when you take a look at what I said here, we're actually going to have B repeated samples. Okay, B repeated sample. And at the end of the day, what do you think? What do you think I'm doing here? I'm finding the average of predictions across the numbers of trees. The numbers of trees here is actually B, which is the numbers of bootstrap samples. Does that make sense? So now when you take a look at the bagging, I want you to see the difference between bagging and random forest. Okay. Even though in bagging we're trying to solve a problem of high variance, the bagging will lower the variance, but it may not be able to lower that variance effectively. Why? Why? Because in all the trees, okay, it did not use the random selection of the features. It used all the predators. It didn't use the random selection of that. Okay? So which means there is still possibility some trees will look alike. When some trees look alike, there's a correlation. There will be correlation among them. When trees look alike, there's not going to be diversity. We want diversity. Does that make sense? Diversity, the more diverse trees are on the forest, the more, generalizable the model is. And that will lead to more predictive power. That is just the difference between the bargain and the random forest. So in the bargain, we did not use the random selection of features. Okay. Now I'm still on the bargain. Okay. And here has a question. Why do we think this lower the variance? In statistics, average has huge power over individual. I'm going to say that again. In statistical framework, average has huge power over individual. And that was why I said we may expect the variance of an average of the different random variable to be lower than the variance of each of them individually. Can I remind you of something? In your linear regression, where you are talking about prediction, right? When you talk about interval for prediction for individual, interval for prediction for the average, which one has a lower variance? It's the one for average. Does that make sense? The interval prediction for average is going to have a narrower interval. Do you know why? What is responsible for the narrower interval is because of the smaller margin of error. What led to smaller margin of error is when the standard error is small. When the standard error is small, the margin of error is going to be small. Why do we have smallest? Why is standard error small? Because the variance is small. Don't forget, the standard error is the square root of the variance. And that's exactly we have been able, and that is why I'm demonstrating here. Oh my God, what am I demonstrating here? I'm only focusing on individual. The variance of S is sigma squared, but the variance of the mean, oh my God, the variance of the mean is sigma squared over n. Take a look at that. I want you to see something now. When I consider individual, the variance is sigma squared. When I consider average, the variance is sigma squared over n. Out of sigma squared over n and sigma squared, which one is smaller? It is sigma squared over n. They're only going to be the same when number of observation is 1. We're never going to have one observation. We're going to choose more than one. So there's a power in the average. Okay? So bargain benefit from the power of average over regression tree. Any question on that? Any question? So it's going to find the average of the regression trees. Okay? And that is what is so, and that was why I said here, when we are given a new observation, we will assign it to the class with the most commonly occurring. Okay, for such value of S over the B trees, if you are working, we have bargain for classification, we have bargain for prediction, depending on the nature of your response variable. The same way we have regression tree for classification, we have regression tree for prediction. Now, you now see the difference between that and that. We normally want a situation where we want the numbers of bootstrap to be more, because when the numbers of bootstrap increases, we do not wish to overfit the data. Of course, in statistics, when we want to estimate the population mean, okay, the sample mean will converge to population mean under the law of large number when the sample size is sufficiently large. We all know that. Okay, the sample mean will convert to the truth. The same way here, we are never going to risk overfitting the data when B increases. when the numbers of bootstrap. So we normally recommend how sufficiently large is the number should be around, should be 100 or 1000. Does that make sense? And that is so what I'm demonstrating here. Okay. Um, we're going to consider cross-validation approach. We are, we're going to train some bootstrap, some part of the bootstrap. Then we're also going to test. Okay. So that is what I mean here. The 2/3, okay, like 2/3 is going to go for the training of the bootstrap samples, go for the training, and one top is actually the one that you not use for the training is going to go for the test. I'm going to walk you through an example here. We're still on bagging. Oh my God, pay attention to what I want to do now. What I want to do now, I actually want to do a classification. I want to do bagging with classification where I got 6 observations originally. And I only want to demonstrate for, meaning I want to have 4 bootstrap. The 4 bootstrap is going to come from the original data set. And the nature of the response variable here, I got 3 classes. 3 classes, 0, 1, 2. I got 3 classes. I need you to pay attention. Okay, please focus on the board. This is the original data set, right? This is the original data set. Okay, now that's original data set. I want to sample from this data set with replacement. Okay, um, if the original data set is 5 or is 6, right? Now I'm going to have so many bootstrap, but let me tell you, look at the first bootstrap. Okay, the reason why you are sampling with replacement, there's actually you're going to have repetition. For instance, take a look at this. Okay, here, do you see Y3 occurring how many times? 2 times. Then there's going to be a particular observation that be not, that is out in a particular bootstrap. Oh my God! Right now, I'm not seeing observation 1 and 6 in the first bootstrap. Can you see observation 1 and 6? There's no Y1, there's no Y6. So Y1 and Y6 are left out. In the bootstrap 2, it is observation 2 and 4, and so on like that. What I'm just displaying right now is actually when the numbers of bootstrap is actually is 4. In the real world, in the real practice, we normally have more than that. I'm just using this as an hypothetical example. So we could have like 100, 1000, but this is just to tell you in each of the bootstrap sample, there's something that is left out. Any question about what is left out? Okay. Now, let me tell you this. What we left out. Oh my God. What we left out is actually what we're going to make a prediction for. We want to classify them into group. Okay. Now, I need you to pay attention. Okay. If you take a look at here, observation 1 and 6 are left out. Then I'm going to compute posterior probability. Okay. For group 1, group 2, or for group 0, group 1, group 2. I said 0, 1, 2, right? Now I needed to pay attention to what I want to do here. Take a look at this guy here. What am I doing here? Oh, there's 2 observations that are left out, observation 1 and 6. I want to compute the posterior probability so that I'm actually going to assign the observation missing to class. But I'm going to base that on the maximum majority rule. Now, the group 0 gives 0.1, group 1 is 0.7, group 2 is 0.2. I'm actually going to use the highest value. Then it means the first that means observation 1 that is part of what is missing here is actually going to be assigned to class 1. Now I've assigned observation 1. It is time to assign observation 6. Then I derive another posterior probability associated with each of the class. And of course, the maximum one is 0.8, which is going to be 0, class 0. Then observation 0 should go, I'm sorry, observation 6 should go to class 0. And we do the same for every one that is missing. Okay? If you take a look at here, it is only one that is missing. Okay? If it is only one that is missing, that will be very, very easy. Now, there is possibility here that I've assigned a particular observation to more than one class. And therefore, we want to have a count. We want to have a frequency of occurrence. Now, I'm going to generate a table for that. Okay? Oh my God. That is what the software, that is what is happening. A lot is happening behind the scene when you are using software that you don't see. Okay, this is a table right now. We have observation. This table actually talk about observation missing. But when you take a look at all of that in the bootstrap samples that I show you, observation 3 is not missing. Therefore, we do not need to classify observation 3. I'm going to show, let's go back and see. Is there anywhere either here or here? No, 3 is not missing. 1 and 6 missing, 2 and 4, 1 missing, 1 and 5 missing. There's no 3 missing. So if that's why when you take a look at 3, I put a dash, dash, dash. It is not missing, then we don't need to classify that. But we now take a look at the count now for observation 1. If you go up, how many times do we classify observation 1 to class 0? How many times? You're going to check here. Okay. How many times do we classify observation 1, okay, to class 0? It's only one time. Do you see here? One time. And that was why I wrote 1 here. How many times do we classify observation to class 1? Okay. Observation 1 to class 1. Okay. Here, 1. Observation 1 to class 1. And here, observation 1 to class 0. How many times? Okay, so when you take a look at all of that in general, this is just telling you the numbers, okay, the counts. Observation 1 was classified as class 0 one time in the entire process. Observation 1 was classified to class 1 2 times. Observation 1 was not classified to class 2 at all. Therefore, if I'm going to use majority rule, then observation 1 should be in class 1. That will be the final prediction here. The same thing also applicable to all of these. Is there anyone who has a question about that table? Is there anyone? Okay, all good, right? You know, you are not likely going to see stuff like this because when you use software, whether Haru or MATLAB or Python or whatever, you're only going to see end results. A lot of things happen behind the scene that you don't see. Okay, now let me now tell you this. I remember in regression analysis, where we are looking at the effect of predator on response, and probably we may want to rank how important is the predator. We also have that here where we call that variable importance. Okay, so the variable importance, of course, we can have a graphical visualization of the most important predators that we use to train the model. Okay, now, and of course, we can measure the decrease of ROSS or the Gini index that we induce by each split over the given predator. And then we average that over the numbers of trees Oh my God. If you take a look at this guy now, the biggest bar is actually corresponding to the most important predator. So take a look at that. This guy, the second, and so on like that. So the first two, three is TAI, CA, and the chest pain. That's what we call variable importance. Okay? So what if you have something like that and they say, what are the most important variables? Okay? That's what you have. Now, let me tell you this. What is the weakness with bagging that will make us to consider random forest? When you take a look at bagging, bagging did a great job, but there's possibility. Situation where some predators are very strong, okay? Then there's going to be correlation among trees. There's going to be correlation among trees. Some trees may look similar. And when they look similar too much, the problem we are trying to address may not be adequately addressed, even though it's still better than the regression tree. Now, what is random forest bringing into the table? Random forest would like to combine, uh, you know, bagging with something. Random forest we combine bagging with random subset selection of features. What is random here is that the features used for a particular tree, okay, random forest will select those features randomly in such a way that the features that is used in the tree may not be the one used in the another tree, and at the end of the day, that will create what I call diversity among trees. Diversity among trees. I tell people around me, I don't know why there's variation, but there's something that I know. There's unity. There is beauty in diversity. Beauty in diversity. When we look the same, when we all look the same, the world may not be beautiful. But we look differently, the world is now beautiful. I can see the kind of cloth that everybody put on today. If put on different fine cloth, it's making this place to be beautiful. That is the diversity we talk about. So right now, the random forest is still using the principle of bootstrap samples, but except that it's actually going to use there's going to be a random selection of the subset of the features. And because of that, we're going to have diversity. Diversity will enable trees not to have correlation. And the moment, and that's what we call decorrelation. Decorrelation is that you are removing correlation. When you remove correlation, the model will be more robust. The model will the model will solve the problem of overfitness, which means it will reduce the high variance, and of course, it will thereby increase the predictive accuracy, and it will improve the predictive accuracy. Okay, now you can see the difference between the random forest and the bagging. They use the same approach, but why in bagging? Bagging use all features in each tree, okay? And trees may be similar. When they are similar, that will induce correlation. When that induce correlation, then we may not be able to solve the problem of high variance adequately. And we bring in a random, the word random in a forest. When you enter, has anybody been to a forest before? How many of you have been to forest before? Oh, okay. I've been to forest so many times when I was in Africa. So, when you get to forest, you don't see the same trees. You see different trees. That's a diversity in the forest. Okay. So the way each tree is being built, they use random selection of features, which induces diversity. Now, and that was what I'm trying to talk about here. We're still using the B bootstrap, okay, to train the data set. But instead of us considering all the predators, we only consider the random subset of the predators. And that's what you see. And what is the formula? Okay, what is going to be the formula? The formula is going to be, oh, if I have p numbers of predators, find the square root, because we want to compress that. Okay, or you do the 1/3 of that. But the question now, why is it that if m equal to p, oh my God, if m equal to p, the random forest now become baggy. If m equal to p, because I'm using all the predators. That's what that means, you're only doing bagging. Okay. Now the question now is, when will we prefer smaller m? I said when we have few predators that strongly affect the outcome. It is not necessary. You know what the random forest is going to do is not going to use all predators, because there's a possibility some predators may actually may have the same statistical power. Okay, now okay, and that's all about the random forest. That's why it is called random. Random now. The random aspect of the forest is the fact that they have a random selections of features, and not all features, subsets of features. So random forest is the same, is combining bagging weight, random selection of subset of predators. Now we want to move right now to boosting. Why do we need boosting? You know, the only problem we're trying to solve with bagging and random forest is the problem of high variance. We're not solving the problem of bias. I'm going to say that again. We're not solving the problem of bias. If your intention is to explain, okay, so using random forest and bagging, or may not be, or may not be okay when you want to explain. But when you want to make a prediction, that's okay. Because the problem with prediction is not a problem of bias, but a problem of high variance. So, and that is why the boosting is coming into play. The boosting is, okay, can we have a way to reduce both the bias and the variance, even though there's a penalty, okay, that's actually going to come with that. So what boosting is going to do is to be updating. Is actually we're gonna have a module that was conducted sequentially, where at each stage you try to correct the errors of the previous stage. I'm going to say that again. At each stage, you're trying to correct the errors at the previous stage. Now here, I said conversely, from bagging and random forest, in boosting, we only use one training set, and no bootstrap is needed. One training set, no bootstrap is needed, and we grow trees sequentially, where each tree is an updated version of the old. Okay? At the end of the day, we're going to settle for a particular one. But each tree is going to be updated of the old one. So which means when we are updating, we are actually correcting the previous error. And I said, here we focus on boosting for the case of regression trees. Okay? Now we can apply the same approach where we're doing classification. And if you take a look at this, in the boosting, if you have a current estimate in terms of days, because you're actually going to, what do you want to boost? If you want to boost something, you start with initial something, and you start boosting that initial, something until you get to a point that you're actually going to say, okay, this is the end of it. Okay. Now I said we initialize setting that prediction to 0, okay? And when we set that prediction to 0, then we will fit, okay? We actually are going to fit, the next decision tree of whatever size, okay, on its residual, okay? Of course, what is residual? The difference between the predicted and, so right now, instead of us to use the response, we are not using response, then we're using the residual, okay? And that was why I said we feed the next tree of the size D on its residual, okay? Now, which means we are initializing at the residual equal to the y high. Now, and that was why I said here, instead of the values of the response, we're not using the values of the response. But don't forget, to get residual, I've already used the values of the response. Residual is a difference between the actual observation and the predicted. I think you know that. Now, we will then update. And of course, if you want to update, let me give you see something like that before, right? The f of s cap equal that plus the lambda, then the new one, then the ROI equal to what you see. That is the algorithm, okay? And the lambda here, we actually represent the shrinkage, okay? We're going to represent, we're going to call that shrinkage parameter, and we can actually choose equal one, maybe probably 0.01, 0.001, and of course, and I said here, the smaller number of split D, okay, we still want to have smaller number of split. Don't forget, if more split means more leaves on a tree. We don't want a situation where you get a tree and there's a lot of leaves. That will overfit, okay? Now, and the lambda, then the slower, the improvement of that. So when we continue, our head boost at the end of the day, okay, it's actually going to be the sum. You can see we're summing from B1 to B, or that the lambda and that particular function, okay? So this is the algorithm that I explained here. They said, step 0 is set that to 0, okay? And find the residual. What is the residual? Y minus the fitted. But do you know why residual is going to be the same thing as y? Because of the fact that this guy is taken to be 0. So then it means the residual is going to be equal to y. That's what you see here. Then you go to step 1. Then you feed a tree with a particular number of split on the not on the one that you used to see, but on the residual. You see that? Then we obtain this. Then you continue to update. Okay? But let me tell you, so there are different kind of boosting that I've seen in literature. Okay? We have gradient boosting, ADA boosting. There's so many of them. Okay? Now, let me quickly come here because of my time. Unfortunately, when performing boosting, large B may lead to overfitting. You can see that? But large B does not lead to that in the bargain. You remember in the bargain? Okay. And this aspect is further aggravated when D is also large. When the D is the number of splits, when you have so many leaves, okay, the problem will be compounded. That's what we mean. So in general, the smaller the D, the larger the B needed to achieve good predictive accuracy. Take a look at that. The smaller the D, that day the number of split. When the number of split is small, the larger, the B needed to achieve that. Now, I think I can also ask you some question in exam about, some things. What do these three have in common? Okay, bagging. We're using just parameter B, the numbers of bootstrap. But in random forest, they are, in addition to the parameter B, the number of bootstrap, we also considering the random selection of the subset of the feature that I'm actually going to call M. Okay. Now, for the boosting, we got three parameter. There's going to be shrinkage parameter lambda. We're also going to have the numbers of split D, and of course, that very B. And I said, we have to select a combination values of those. And that we can use cross validation and so on like that, to come out with the boosting that is actually going to work. And of course, with the bargain and random forest, I said in random forest, the trees are not pruned. Don't forget, in the regression tree, we prune. Why do we prune? We don't want the tree to overgrown with leaves. But in random forest, we don't do that. Okay. And I said this will lead to high variance, but averaging over many big trees, okay, and choosing the random subset of selection will reduce that. Okay. And of course, we have a way to compare between modules. We can use the test mean square error for prediction and error of classification, for classification problem. Now, this is the end of this particular material. Is there any question before I go? Like I said, you're gonna get your booklet on Friday, and of course, before that Friday, you're gonna see your results posted. So if I'm going to require makeup, I'm going to see, because I normally consider makeup when the performance is not satisfactory. So when the performance is satisfactory, then I don't need to consider student for makeup, except if there is extraordinary circumstances, because I do not have power to control the world. Anything can happen. So okay, is there any question before I go today? It's another Friday, and we're moving gradually, to the final exam. And just like what I used to do, I'm also going to release a practice question shortly. Make sure you all stay safe and have a lovely day. Bye for now, everyone.